I want to add one more note in before we move on to the next definition. And what this note is saying, roughly speaking, is that this whole concept of two vectors being parallel, it's a transitive relationship. And here's what that means mathematically. So up here, this is what it means. This is how you would briefly say that you have two vectors, x and y, that have the same number of coordinates. Well, now I'm going to do that for three vectors. So I'm going to say if x and y, and I'm going to use z for the third vector. So x, y, and z in Rn, which is just an abbreviated way of saying that we've got three vectors, x, y, and z, and they all have the same number of coordinates. So if these three vectors are such that x is parallel to y, and y is parallel to z, well, if that's the case, if x is parallel to y and y is parallel to z, well, it turns out that x is going to be parallel to z as well. You don't even need to check that. You get that for free. So that's what we're going to put here at the end to finish the sentence. Then x and z are also parallel. So that's the transitive property that the whole concept of two vectors being parallel possesses. Okay, so the next definition is really a matter of notation. I'm not really going to define anything new. It's really just a label for something that we already have access to. But these are special vectors now. We label them as E1, E2, all the way up to En, where n, this final index is going to be, well, it's going to be whatever dimension that you're working with. So if we're dealing with R3, then you'd only have 3 vectors in this list. If you're dealing with R10, well, then you're going to have 10 vectors in this list. But no matter what the case is, these vectors have a special name, and they also have a special definition, which I'm going to fill in below. But let's start with the name. These are called the standard basis vectors. So the standard basis vectors of Rn, and they're the standard basis vectors of Rn because they live inside of Rn. So if n is equal to 3, then you'd be talking about the standard basis vectors of R3. If n was equal to 7, you'd be talking about the standard basis vectors of R7, and so on. So n is just a general positive counting number, as usual. So that's what these are called, but what are they? They're actually, you can write them down as coordinate vectors in the following way. The first vector, and actually, let me pause. Before I write them down, let me just tell you what they are in as brief of language as possible, and then we'll write them down in a more rigorous fashion. So all of these vectors have the property that all of their coordinates except for a single one are 0. And the only non-zero coordinate is equal to 1. And lastly, the location of the non-zero coordinate, which happens to be a 1, is given by the index. So with that in mind, let's write down the first vector, E1. And if that didn't make sense, don't worry about it. I'm going to write the vectors down officially just now, right after we're done, and then you can think about it afterwards, and then it should make more sense. So let's write down E1. So it's got n coordinates, because it's a vector in Rn, and its first coordinate is a 1, and every other coordinate is a 0. So it's 1, 0, 0, and so on, all the way up to the last coordinate, which is also a 0. Then your next standard basis vector, E2, well, the second coordinate is equal to a 1. That's what this index really tells you. And then all of the other coordinates are equal to 0. So it's going to look like this, 0, 1, 0, and just keep writing zeros until you get to the very last coordinate. And you carry on in this fashion. So E3, well, the third coordinate would be 1, and every other coordinate would be 0. And keep on following that pattern until you get to the very last one, which is in general will be En. And it's, well, the nth coordinate, in other words, the very last coordinate, is equal to a 1, and every other coordinate is equal to 0. So it's going to look something like this. And then when you get to the very last coordinate, it's equal to 1. Okay, so that is the definition of the standard basis vectors. And they're really handy to have from a notational standpoint. So we won't use these immediately on this page, but we will on the next page, and then their main feature will become clear at that point. But for now, this is just notation. Okay, so we're moving on now to a new idea called linear combinations. So the first thing we're going to do is define a linear combination. So before we write anything down, I just want to mention the definition of linear combination requires, before you can even formally say it, you have to have a handful of vectors already in existence in the background before the definition is going to really be phrasable or even make sense. So that's what we have over here. Okay, so we've got a vector x1, a vector x2. So then, as you can see, I've got dots here. So it goes on, it's a list, they're separated by commas, so we're making a list of vectors. And the very last vector in the list is xk. So the index is given by k of the last vector. So k really is the number of vectors in this list. And they're all vectors in Rn, which means each one of these vectors, because each one of the vectors in this list, they're all going to be vectors, they're all coordinate vectors, and they've got n coordinates. So n is the number of coordinates in each of these vectors, and k is the number of vectors in this list. And I know that they all have n coordinates because they're in Rn, right? Okay, so this new term, linear combination, that's what we're going to say here, a linear combination. A linear combination of these vectors. So these are understood to be fixed in the background. These are not, we're not defining these vectors. They would have to already be given to us before we can talk about a linear combination of those vectors. So what is a linear combination of these vectors? Well, it's something that you can build in the following way. Okay, it's just something that looks like this expression here. And what is this? Well, we've got each one of these vectors in the list, right? And each one of them is multiplied by some scalar, right? So it's anything that you can write in this form for some choice of scalars, C1, C2, all the way up to CK. So, I mean, really, this list of scalars is just there to ensure that each one of these vectors, x1, x2, all the way up to xk, they all have their own scalar. They can be multiplied by any scalar at all, and then they get added together. So you've got a scalar times the first vector plus a scalar times the second vector, all the way to the very last term here, which is just any scalar times the very last vector. The reason for the notation, C1, C2, all the way up to CK, is just to keep things organized. But the way you should think about this is just simply a linear combination of vectors in any list is something you can build, and you're free to multiply each of the vectors by absolutely any scalar value that you please, and then add them together. Okay, so that's really what a linear combination is. So it's anything of this form where you're allowed to choose these values to be anything you like. And these ones are just fixed in the background. So that's a lot to unpack in this definition. So let's look at an example. And the first one I'm going to show you is the vector 13, 12. And I'm going to claim to you that this vector is a linear combination of 1, 2. So the first vector is going to be 1, 2. The second vector is 2, 6. And the third vector is 4, 0. Okay, so that's my claim. Now, just because I say it doesn't make it true. All right, and how would we check? How would we check if I'm lying to you or not? Or if you believe me, how would you check that what I'm saying is really true? Well, let's look at how this claim even fits within the form of this definition first. So really, what are the xk's? What is k even? What is n? What are the c's going to have to be? Right? Those are the questions that we have to answer in order to really say that this is a true statement. So the first thing I want to point out is that this list of vectors is really playing the role of this list of vectors. So this one here, let's say this is x1, this is x2, and this is x3. Okay, so really our k is equal to 3 in this case. And n, remember n is the number of coordinates that each of the vectors has. So since they each have 2 coordinates, I'm writing these vectors in as column matrices, which is a valid notation to use for vectors. But these are all 2-dimensional vectors, so n is equal to 2 in this case. Just to understand, there's an important distinction between what k what k tells you and what n tells you. N is telling you the number of coordinates in each vector. They each have 2 coordinates. And k is telling you the number of vectors in the list, which is 3. Okay, now why is this true? How would we verify that this statement is true? Well, you have to be able to show that this vector can be written in this form. But if you actually know what the vectors in this list are, that's going to make this a lot more specific. But remember, it just means that we can write this vector as some number times this vector plus some number times this vector plus some scalar times this vector, a scalar in each case, right? A scalar times x1 plus a scalar times x2 plus a scalar times x3. So if I can give you scalars that make that work, then that's sufficient to justify this statement. Okay, so well, let's do that then. Let's give the reason. So because the vector 13, 12, and I'm just kind of pulling these out of nowhere. And if you're not sure where I'm getting these values from, that's totally okay. I haven't shown you that part. I really just want to show you what it means for this vector to be a linear combination of these 3 vectors. But I'm not going to actually tell you how I'm obtaining these scalars at this moment. I'll do, before we get to the end of this section, I'm going to show you an example where I tell you how to do that. But for now, I'm just going to give them to you. So I can write the vector 13, 12 in the following way. I can write it as 3 times x1, right? That's x1, because this is x1. And then I'm going to multiply the vector x2. I'm going to multiply it by 1. So plus 1 times x2, which is 2, 6. And then I'm going to multiply the vector x3 by 2. And that is the reason. Now, is that true? How do we know that's true? I didn't actually work it out in detail. Well, I would invite you to pause the video right now and just double check, right? You can just multiply the 3 into these 2 coordinates, multiply it in, take the 1, multiply it into this vector. It's not going to do anything because it's just a 1. Then take this 2 and multiply it into this vector. And then you've got 3 vectors that you can add together. It's just like if you were adding together matrices. And essentially you are adding together matrices because column matrices are nothing but vectors, coordinate vectors. So you can carefully work out the right-hand side and check that you're actually going to get exactly the vector 13, 12 if you carefully work out this vector arithmetic. So I'll leave it to you to do that as an exercise. But once you've done that, I'm assuming now that you've gone ahead and done that if you weren't convinced, but now you are convinced. And let's look at what these numbers are. 3, well that's C1 because it's the number that multiplies onto x1. And C2 is going to be 1. Because that's multiplying on to our x2. And then C3 is 2 because that's what's being multiplied onto x3. So that's what's happening here. So let's just mention that to be complete. So C1 is equal to 3, C2 is equal to 1, and C3 is equal to 2. So now, I know I've already said this, but it's important, so I'm going to emphasize it again. I haven't told you how I came up with these 3 values, C1, C2, and C3. It's one thing to write this statement down and then check in hindsight that it's true. But how are you supposed to come up with a statement like this in the first place? If you were trying to determine, let's say, whether or not this vector is a linear combination of these 3 vectors, well then you'd have to come up with the 3, the 1, and the 2. Or maybe it's not possible, but you have to be able to decide that. So I haven't shown you that yet, but don't worry, stay tuned, and that will be coming on the next page.